Okay, so let's have a look at some past paper questions. This one is June 2016, Module 5, the AQA Legacy, the old AQA specification, but the style of questions hasn't really changed at all. Let's have a look at this question then. Right. Identify the weakest oxidizing agent in Table 2. Well, we have to think on the left-hand side of the arrow, we have well, those are all the things which can move forward and take in electrons. Oxidize, so they're oxidizing agents. Oxidizing agents take in electrons, get reduced themselves. On the other side of the arrow, so all the Zn, cobalt, water, and so forth. On the right-hand side, they're all reducing agents. So which is it says the weakest oxidizing agent. Let's just think, what's the strongest oxidizing agent? It's going to be the cobalt, because that is the most positive value. So that's going to be the best at pulling electrons in, because electrons are negative, so the most positive value is going to be the best one. So that means the weakest oxidizing agent is the most negative one there. So that's the zinc 2+. That's not a very good oxidizing agent. Right. Next question then. Right, let's now look at two half cells involve the species are connected together to give a cell with an EMF of 0.48 volts. What are those two half cells? So remember that E cell is equal to the right hand side, the potential of the right hand side, E right minus E left. That's the equation. So we're looking for a gap of 0.48, and I think the only ones that work there are these two. Yeah. So let's put that in. Now the right hand side electrode we always put is the most positive. So that's the most positive. And the left is always the most negative. So the most positive is the cobalt one, 0.28. So it's minus 0.28 minus, take away the negative one, minus 0.76. That's equal to plus 0.48 volts. Okay, deduce the conventional representation of this cell. Okay, so let's do that. So looking at these two, first of all, start with our salt bridge in the middle. Convention, we said put the positive on the right. So the most positive is the cobalt one here. So I'm going to put CO2+ and then CO. Why did I put the 2+ next to the salt bridge? Well, that's because it's the oxidized species always goes to the next to the salt bridge. That's the convention. A straight line here because we've got a phase change because it's cobalt metal. The left-hand side electrode, that's a negative one. That's the zinc one. So oxidized form next to the salt bridge, Zn2+. Phase change again because it's Zn aqueous ions and then that's Zn metal. Right, so that is our equation there. And then it says write the half equation that occurs at the negative electrode. So which is the negative one? We've established it is the zinc one. Now, what direction is that going? Let's think. Okay, so is it going forwards or backwards? Well, let's look at our two equations we're interested in, the zinc and the cobalt. Which is the most positive? It is the cobalt. That's the one that's going to be forward, taking in the electrons. The zinc is the one the most negative, that's pushing electrons away. So that's going that way. So the answer to that, this one is half equation, which occurs at the negative electrode, is Zn is going to Zn2+ plus 2E minus. Okay. Right, we'll move on. Right, use the data to identify a cobalt species that can react with water. Right, now where have we got water in that equation, in any of those equations? Well, we've got water here. So water there, that's on the reducing side, isn't it? So that's got to react with something on the oxidizing side. So what the oxidizing side is here then, which, well, we've got two cobalt species on the oxidizing side here. We've got that one, cobalt 2+, and that one, cobalt 3+. Which one is the right one? Which is the answer? Well, let's suppose we chose the wrong one. Let's say we think it might be cobalt 2+. Well, we'd have to have a look at these two half equations, and we say which direction is it going? Well, the cobalt is the most positive. The oxygen is the most positive, so that would go that way, and the cobalt would go that way because it's the most negative. And we can see that that's making water. The water is not reacting, so it's cobalt 2+ can't react with water, so it must be cobalt 3+. Let's just check that. Right, so we're looking at these two equations. Out of these two, which one's going to go forwards, which one's going to go backwards? Well, the most positive one is this one, so that one will go forwards, and this one is most negative, so it's pushing the electrons out, so that will go backwards. So the answer is cobalt 3+ will react with water, and it will turn the water into oxygen, and it will get reduced itself to cobalt 2+. Write an equation for the redox reaction that occurs and identify the oxidation product. Okay, so what we've got to do is combine those two half equations. We know which one's going back, which is going forwards. You have to be a bit careful. This one is only 1 electron. This one is 2 electrons, so we need to times this one by 2. So we'd have 2 cobalt 3+ plus water turns into, right, we get cobalt 2+, and then we get these products here, so we get a half an oxygen and 2 protons. The question says, what is the oxidation product? Well, the oxidation product is the oxygen, and we can tell that because the oxidation of oxygen in water there is -2. The oxidation number there is 0, so that's been oxidized. The hydrogens haven't changed. They're not the oxidation products. That's a +1 oxidation state in the hydrogen there and a +1 there. So oxygen is the answer there. Right. Sorry, I'm going to copy that one down twice. So we've done that. That's the end of that question. All right, let's move on to the next one. Right, this is the 2015 question from the 2015 paper, module 5, and the legacy again, the old spec. Where they say similar questions in still on the new specification. Oops. Right. Okay. So, right. Let's look at this 6A then. Yeah. What is the meaning of the term oxidizing agent? Well, an oxidizing agent is something that accepts electrons. And in doing so, it gets reduced itself. Right, identify the weakest oxidizing agent. All right, let's go. All right, the weakest oxidizing agent in table 6. So we need to identify which ones are which side of the equation are the oxidizing species. So these are all the oxidizing agents, potential oxidizing agent on the left of the arrow, and the potential reducing agents are all on the right of the arrow. Actually, I just noticed, and they always do this, is in the previous question we had the most negative at the top of the table, and it went down to the most positive. They've done it the other way around here, and they always do that. They always switch it. They always change the order, you know, ascending order one question, descending order the next. So be careful and make sure that you notice which way around it's going. Okay. Right, write the conventional representation of the cell used to measure the standard electrode potential of the Ag+. Okay, so whenever you measure the standard, whenever you want to measure the standard electrode potential of something, you can connect it to the standard hydrogen electrode. And if you remember, the standard hydrogen electrode always goes on the right-hand side. So I'm going to draw here's my salt bridge, and I've got to put the standard hydrogen electrode on the right-hand side. The standard hydrogen electrode, you've got 2H plus and 2 electrons goes to H2. So the oxidized form is the H plus ion, so that's going to go there. H plus. Now we need to draw a phase change because we're going to have a gas next. Hydrogen is the reduced form, and we'll also need platinum. So another phase change, and we've got PT there. Right, let's do the, so we need to connect that to the electrode of interest, which is the silver electrode. So oxidized form there, and the reduced form there. Phase change because you've got silver ions and silver metal. Okay, and just to remind you, why do we always put that there? Why do we always put the standard hydrogen electrode on the right? Well, the reason why is because, remember, E cell is equal to E right minus E left, and of course the definition of this one is 0, isn't it? So, you know, it's going to be the value for silver, which is 0.8 minus 0, and you know, E cell is the same as the electrode potential of the one that we're comparing against hydrogen. Okay, state the conditions necessary when using that cell. Well, it's standard conditions, so it's going to be 298 Kelvin, 1 atmosphere pressure for the hydrogen, that's important, and the concentration of the H plus ions, all ions, H plus silver at 1 mole per decimeter cubed. That is the standard conditions. Right, so we've got to use the data from the table now, I think, for these questions. Use the data in the table 6 to explain in terms of redox what happens when a soluble gold 1 compound containing Au plus 1s is added to water. State your observed and write an equation. Right, so we need to look at this equation. So where is Au plus here in this equation? That's the only place we see Au plus. That's on the oxidizing side. These are all oxidizing sides. These are all reducing on this side. That's going to react with water. So the water, we've got to be looking for water on the right-hand side of the equation. Right, it's not this one because that's got chlorine as well. So forget about that. The one we're interested in is this one here, this half equation. So these are the 2 half equations we're interested in. Okay. All right, so what happens when you add it to water? And we need to write an equation for this reaction as well. So we'll probably write the equation first and then we'll say. So which one's going to go forwards? We've got to think about this half equation and this half equation. The most positive is the gold one, so that's going to go forwards, taking in the electrons, that's right. And this is the most negative, so it's pushing the electrons away the strongest, that's going to go that way. We need to balance this because look, we've only got 1 electron there, so we've got to times this one by 4 because this one has got 4 electrons. So we would write down 4 Ag plus 2H2O goes to 4, it's not Ag, Au, beg your pardon, gold, goes to, and that's going to go to 4 Au metal plus oxygen plus 4 hydrogen ions. So what would you see? Well, you'd see a precipitate of gold, and you would also see, you've got oxygen there, so you'd see some fizzing, some effervescence. Okay, that's what you'd see. Right. Rub some of this out. Okay. why a potassium chloride salt bridge would not be suitable for this reaction. Well, oh sorry, I missed the question out. A cell is made by connecting Fe2 plus and Ag plus electrode with a salt bridge. Calculate the EMF of the cell. So E cell is equal to E right minus E left, which is the right. It's the most positive one. Which is the most positive one? So we're talking about the silver and the. Now we have to be careful. Fe is this one here. It's not that iron one there, is it? Not that one. So the most positive is the silver one. So it's going to be plus 0.8 minus the iron one minus 0.44, which is equal to 1.24 plus 1.24 volts. It's plus. It's if you make the E right, the positive one, then it's always plus, isn't it? Right. So this question: now, why would potassium chloride not be suitable for use in this salt bridge? Well, let's see what we've got here. We've got silver ions and Fe2 plus ions. Now, can you think, is there anything in potassium chloride that's going to react with either of those two? Well, you may remember your group 7 chemistry, right? Ag plus will form a precipitate with halide ions. You get AgCl precipitate. So that would be no good, because you'd want to keep your Ag solution at 1 mole per decimeter cubed, because that's the standard conditions. Or if you added if you got some chloride in there, it would precipitate out the silver, and the concentration of it would drop, and it wouldn't give you an accurate result. Right. Use the data from table 6 to explain what happens when you add iron 2 chloride to the air, expose it to the air. Right. So iron 2, we have to be a bit careful there, because we've got two equations we could be interested in. We've got that one's got iron 2 in it, right? This one's got iron 2, and this one has as well. Now in the air, what's it likely to be in the air that's oxidized, that just giving the game away, which reacts with things? That's the oxygen. So it's that equation. Okay, so we're looking at the oxygen. So the oxygen is an oxidizing agent. So the Fe2 needs to be on the reducing agent side of things. So it's not this Fe2, because that Fe2 in that equation is acted as an oxidizing agent. It's accepting electrons to go to Fe. So it's not that one. It must be the other one, because that's on the reducing side, this one here. Okay, now what would happen with iron 2? Well, let's have a look at these two equations. Can oxygen react with Fe2? Well, which is the most positive of those two equations? It's the oxygen one. So that's the best at taking in electrons. So that's going to go forwards. Which is the most negative? It's this one, which is the best at giving away electrons. It's going to backwards. So, so what would happen is the oxygen will oxidize Fe2 plus to Fe3 plus ions. It doesn't ask for an equation there, so we won't give one. Okay, and I think that's the end of that question. That's the last bit.